Try. Yeah, if you're having trouble navigating that table, there's only one equation or half reaction that has ClO2 in it. That kind of helps. In fact, I believe there's only one that has Cl negative in it. You get these two half reactions? That's right. Add these two together. Now, before we add them together, we need to make sure that it's balanced, which means it has to be balanced for atoms and for charge. Right now, they're not balanced for charge if we add them together. This takes in 2 electrons, but that only gives off 1. That's not good. So, and Sonia, that's what I was talking about. If we take in 2 electrons, this has to give off 2 electrons. So we have to multiply this through by 2. Yes? And when you multiply this through by 2, what do you do with that? Nothing. Don't do anything with it. And I know, as you do these problems, it's going to feel strange or not right that you're not doing anything with this even when you manipulate that. But it's correct. Because that naught sign means that all your concentrations are 1 molarity. So it doesn't matter what the coefficient ratios are. They still have the same concentration. So anyway, your N value in this case, the number of electrons that are transferred, is 2. Just the number of electrons in the balance equation. So we now have what we need. We have delta G equals negative 2 moles of electrons times 96,500 on the F value. That's coulombs per mole of electrons. And then the epsilon value is that plus that, which is, I'm just going to round that to the hundredths place, 0.41 volts. And we're going to get something around negative 79.9. I used 96,485 when I calculated, so I got negative 79.9. So we may be off by a little bit. Oh, and by the way, this gives you joules. I'm using kilojoules. The volt, remember, is joules per coulomb. That's how they canceled. So yeah, you get 79,000 something, and I just rounded and cut that down to kilojoules, 79 kilojoules. Negative. How'd we do on that one? So this equation, when you do some of these, it's not bad. There's a little bit of hunting on the reduction potential table. You'll figure out where stuff is. In the next 2 slides, I'm going to ask you to rank the things that are the best at reducing to the worst at reducing. That's what I am asking on this slide. The next slide is going to be rank the things that are best at oxidizing to the worst at oxidizing. This first slide is the easier one. So we're going to get warmed up with this. You have to use that table, find the reduction potential of each of those 5 things, and rank them. Best at reducing to the worst at reducing. No, you have to use the chart. There's no way you can tell. Can you find all of them? They'll all be on the reactant side. Here are the reduction potentials I'm hoping you'll find. And from here, if we want the best at reducing, we'll take the most positive reduction potential. Down to the worst at reducing would be the most negative reduction potential. So ordering them should go like this. Yes? Okay, now I warned you. Hopefully your brain is lubricated, and we're going to try the next slide, in which we want to order the best to worst oxidizers. Everybody good on this one? Okay, try this. Here are 5 things. Figure out their oxidation potential and then order these. Remember, you're looking for these things on the right side of that table. All the reactions, they have to be products of reduction. So you're looking for them in the products of the half reaction. Turn them around, change the sign. The worst one up here is water, because water shows up in a whole bunch of products. You got to figure out. You want to find a reaction which just has water in the products, but there's actually two of them. Now I'll tell you, the water that you want to use is the one that's in the middle of the first column. Not the one that's toward the top of the first column, the one that's in the middle. You see it? This is a hard exercise, isn't it? It just takes a little bit of time. Here are the oxidation potentials I'm hoping you'll come up with. So we order them like this. Just one quick thing about the water. You had two choices. Well, you had a whole bunch of choices on the water, but water is an incidental product on a whole bunch of those. But then the two half reactions that reduce to water, toward the top there's the hydrogen peroxide, and then in the middle there's the oxygen that's reducing to water. Don't ever assume that water will oxidize to hydrogen peroxide. That one toward the top, that is very unlikely. Hydrogen peroxide is a super unstable substance, and don't expect water to oxidize to that. It is an oxidation, but it's not physically likely to happen. What's much more likely to happen is that water, the -2 oxygen in water, will oxidize to 0 in O2. That's that middle 1.23, this one, that half reaction. Okay, so you'll have water a lot. When you go to the exercises, you'll see there's a whole bunch of them that will involve you finding the oxidation potential of water. Use that 1.23 every time. Negative 1.23. Anybody have any questions about these? Okay. Now, so just a little bit of time left in class. What I'd like to finish with is how to deal with problems that are not at standard conditions. You know, we use this table, but the table is not really very beneficial to us, knowing that it's only good for standard conditions when all of our concentrations are 1 molarity. It's very rare that we could have that set of conditions, because as soon as the reaction starts, even if you set it up so that all the reactants and products are at 1 molarity, as soon as the reaction starts, they're not at 1 molarity anymore. The reactants get used up, the products get made, and so they're different now. So it's very tough to deal with knowing that, that table is only good for standard conditions. We're going to have to come up with another formula that we can find the potential with if we're not in standard conditions. So that's what this is going to get us into. So right now, I have a solid in the reactants, and that doesn't have a concentration. But then I have 3